Hi. So what I'm going to talk to you guys about today is the general principle of inclusion and exclusion. This is a good time to present this material because we just talked about combinatorial proofs. So we know that one way to prove an identity is to show that uh, the left-hand side and right-hand side of some expression count the same collection of objects. So we've already seen some miniature versions of the principle of inclusion exclusion, where if you take the union of two sets, right, and we wanted to find the cardinality of A union B, we could find this by taking the cardinality of the individual sets and then subtracting off their intersection. And so I don't want to belabor this too long, but it's worth thinking a little bit about why we do this. If we go ahead and just add it to, or sum together the individual cardinalities, the objects over here and the objects over here will be counted just fine. They'll be summed. They'll be counted once each as they deserve, but the objects here will be counted twice, which is more than what we want. And so in order to make sure each object is counted exactly once, we subtract off this intersection, and that leaves once for each object. And then we did have a three-way PIE identity where you could find this cardinality by summing together the individual sets, subtracting off the intersection of two sets, and then adding back in the intersection of three sets. And now the idea here is if you have objects in the middle here, it's triple counted when we add together the three sets, so that's no good. But when we take away the three intersections, it's now not counted, right? It was counted three times, it was anti-counted three times, and to balance things out, we need to put one back in. The elements over here will be fine. They're double and removed. The elements out here will be fine. They're counted the first time. So after we do the summing, subtracting, summing again, uh, every element is counted exactly once as we hope. And you could probably guess how this generalizes to, if it was 100 or 1,000 or a million sets, it would be a similar dance of add cardinalities, subtract unions of two, add unions of three, subtract unions of four, add unions of, intersections, add intersections of odds, subtract intersections of evens. But if we want to show that this works for any n, it does require a general argument to see why that is, i.e. a proof of some sort. And so the principle of inclusion exclusion we're trying to prove here, in its general form, is going to be something like uh, consider sets x1 through xm, and the whole idea is that the size of the cardinality of the union of the xi, that's going to be the sum. Let's use a different index k from 1 through n minus 1 to the k plus 1 m sub k. And what we want m sub k to denote is the sum of the cardinalities of all k intersections of the xi. So m sub 1 would be the intersections of one element, one of the xi. In other words, just the cardinality of each xi. Then m sub 2 is the sum of all the intersection of two of the xi, every pair of xi's. And then m sub 3, we would take all triples of the xi, take their intersections, and sum those cardinalities. And so we get here is that alternating sum. We add in the 1, subtract off the 2s, add in the 3, subtract off the 4. And we notice that k plus 1 is even when k is odd and odd when k is even. And that ensures that minus 1 to the k plus 1 is positive when k is odd and is negative when k is even, right? And the claim is that these two expressions are the same. And the way we're going to show that they're the same is the same intuition, fundamentally, of what we did over here. What we want to show is that, hey, the union should only count each element once, the cardinality union, sorry. And so whatever this right-hand side thing is doing, it should end up counting each element once. So let's go ahead and draw a picture of what this might look like. This is going to be pretty ugly. So let's say m sub 1, m sub 2, m sub 3, dot, 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 dot. M sub, sorry, these aren't m, these are x's. This is xn, dot, 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 x1, x2, x3. Right, and we're unioning a bunch of these things together. So I'm going to go ahead and pick just an arbitrary x in this union. It could appear in just one of these sets. It could appear in a bunch of them. We don't know. Right? The point is that I should be able to develop an argument for every x, no matter where it appears in the set, to show that the right-hand side, this thing over here, counts that x exactly one time. So I'm going to go and start that argument here. And we're going to let x again be in the union of the xi. And suppose x is in M of the xi. So m is some number between 1 and n inclusive. It could be in all of them. It could be in just one. We don't know. But we know it appears in some of them, right? So I'm going to, for shorthand, refer to this expression as the left-hand side and to this expression as the right-hand side. So note that, well, the left-hand side counts x once, right? Just one time, just the size of the set. So our goal now is to show that the right-hand side does the same. We want to show the right-hand side does as well. All right, let's get to it. So I just want to take a moment to think about what happens on the right-hand side. When we start when k being 1, we're just counting the 1 sets. And how many times does it get counted then? Well, if it's in just one of these xi, it'll get counted once. But if it's in like 20 of them, it'll get counted 20 times, once for each of the xi that appears in, right? If we go back here, the green dots get counted in one of the 3, the orange dots in 2, and the blue dot in all 3, right? So in general, when we do this first summation, it's going to get counted m times, right? Once for each of the sets that appears in. So we'll know the right hand side counts x. Well, first we start with m times, but what I'm going to do is write that as m choose 1, right? M choose 1 is just m. And that's because we want to generalize the argument we're making here to something broader. All right, so that's what happens when k is 1. What happens when k is 2? Well, we now have to subtract off every time x appears in a pair of the xi that it lives in. And how many, let's say that's these guys over there, how many different ways are there for x to appear in a pair of xi's? Well, it could only appear in pairs between the different xi's that actually contain x. So that's m of them. And how many such pairs are there? Well, there's a pair for every ways I could pick any two of these things, right? I have a bunch of xi's that contain x. I pick any two, and they both contain x as well. Or the intersection does, rather. So, right, again, maybe going back to here, if I'm in the green dot, then I don't appear in any of the pairs, I guess. If I'm one of the orange dots, I'll appear in one of the pairs. And if I'm the blue dot, I'll appear in 3 choose 2 pairs. The number of ways I could have picked 2 sets containing the blue dot. So in other words, I'm subtracting off m choose 2. It's anti-counted m choose 2 times, right? Once for each pair of the m sets that xi lives in. And then we could see that when I go back to counting again, that every triplet appears in, I'm going to throw it in, and so on and so forth until m choose m. Now, whether or not this is an addition or subtraction depends on m's sign, right? If it's odd, then we're adding on. If it's even, we're subtracting off. And so now our question is this thing 1? We'd like it to be 1, but we don't know that, right? That's the thing we're not sure about. What I can do is maybe rewrite this in a form that's perhaps less, more compact. We could rewrite that as minus 1 to the j plus 1, m choose j, and we can ask ourselves now, is this thing 1? So that's one way to rephrase that question is, if I took 1 and subtracted off this thing, do I get 0? If I get 0, then this thing here has to be 1, right? There's nothing else I could subtract from 1 to get 0. If I get anything other than 0, then it's probably not 1, right? So why don't I go ahead and begin that? So I'm going to go ahead and say, hey, let's take 1 minus the sum from j equals 1 through m minus 1 to the j plus 1, m choose j. Well, one thing for sure that I notice is that I have a negative here. Sorry, I'm going to stop with that. Now I'm pretty close to that. I have a negative here. I have minuses here. There's probably some simplification that could occur in this step. So maybe what I could rephrase this as is 1 plus a sum from j being 1 through m of minus 1 to the j without the plus 1 here, sorry, j, m choose j. And then what's interesting about this is, sorry. What's interesting about this is that this one, I mean, okay, sorry. The J, as you see, the index from my summation, that goes from 1 through M. And it would be, we have very interesting identities that involve going from 0 to M of sums of binomial coefficients. And what's significant about that is that this 1 here, well, that's simply M choose 0, right? Any number choose 0 is just 1. And so what I have here is M choose 0, and then starting from J being 1, M choose 1, M choose 2, M choose 3, M choose 4, sum together. I can gather all this stuff up together and rewrite it as the sum from J equals 0 to M minus 1 to the J, M choose J. And then here's the kicker, here's the punchline. By the binomial theorem, which many of you used in your last homework assignment, this is equal to 1 minus 1 to the M, right? These are two things here are my x and my y. X is 1 plus minus 1 being y to the M. When I expand that out, I'll get 1 raised to index, which is just 1, and minus 1 raised to an index, which we can think of as this J here. And of course, whatever M is, 1 minus 1 is 0. Right? And that means that the right-hand side also counted x just once. And remember, we didn't care how many of the xi's it laid in. Like, we let M be whatever it needed to be. So that means every single element is counted exactly once. So, therefore, the right-hand side counts each x exactly once, and therefore these two identities or these two expressions here, they count the exact same collection of objects, and therefore they must be the same. Sorry. Plus y. And there we go. And they're proved. Well, thank you. I hope that was helpful. Thanks for watching. As usual, if you have any questions about this or anything from that we're working on right now, from the homework or from the reading or from the other videos, be sure to let me know. Post in the discussion board. I'll happily respond and help everyone out with what's going on. Again, thanks for watching.